So welcome to the last talk that I'm going to share with my colleague Flavio. And for the first half, I'm going to give a hopefully coherent summary of the two works I did with my two supervisors, Stefan Wolf from Lugano and Czaslaw here. And while we have talked extensively about Renato's criterion of consistency and non-alternative facts, I thought I would talk about the quantum theory criterion a bit. So I'm first quickly gonna review the problem in Wigner's friend type paradox due to what I would call a subjective collapse. Then see why this gives rise to the inconsistency and in whether it can give rise to a contradiction. And the main part of the talk is actually the third part where I introduce this, generalization of the Born rule Stefan and I propose for fully unitary quantum theory. Okay, so what I'm gonna say will mostly, for reasons of time, refer to the simplest Wigner's friend type experiment and the one Czaslaw already proposed. The arguments equally apply to the Frauchen-Renner setup unless I say otherwise. So yeah, the simplest version, we've been over this, is the source emitting a plus state, the friend measuring in the Z basis, and then Wigner measuring in this Bell type basis, expecting to see either outcome plus or minus. And if you then ask what are the probabilities for Wigner's result, the friend, if she assumes she is in one of the product states due to having seen one definite result or the other, will predict that these two outcomes should occur with equal probability. Wigner, to whom this joint system evolves unitarily, would say that a plus state by the source will get deterministically mapped to the plus state here and therefore expects to see probability 0 and 1. The nice part about this version of the experiment is that, as Czaslaw already mentioned, in principle, these two contradictory predictions can be exchanged between the two agents, which is not the case for the Frauchen-Renner experiment. And if you scale this up, as Czaslaw also already said, you can get an arbitrarily close to 0, 1, 1, 0 contradiction.
Can I just ask you to say a couple more words on why these predictions are contradictory, given that they're ostensibly about different measurements?
What do you mean by different? They are about Wigner's measurement. They are the predictions for Wigner's outcomes plus or minus.
Oh, okay, so the friend is making predictions not about her spin, but about
Wigner.
The measurement that
Yes.
Wigner is ostensibly performing
Yes.
on the friend
Yes.
plus system.
Yes.
Okay.
Okay, so there are clearly consistent descriptions of this setup, where descriptions that give rise to consistent predictions, so that the agents will not disagree. One is objective collapse, where by collapse I just mean, without ontological commitment, now just application of the state update rule for absolutely every measurement that takes place. So for all the friends and the super observer and every other level of observer you might think of, any measurement induces this collapse, if you want to. Then there is no collapse, which I would like to focus on. And of course, any, I would say, agreed upon combination of the above, so that all agents agree on when I should apply the state update rule and when not. Then I will also not get contradicting predictions. The problem comes if the agents disagree on when to apply the state update rule and then actually make predictions based on that.
So can I just still ask a question about actually following up on this contradiction? So if I understand correctly, the friend makes the prediction that all outcomes are equally likely, essentially.
Yes.
But then just one outcome occurs. It happens to be the, let's say, full zero sequence, but that's just one out of 2 to the n, if you repeat it n times sequences that are all equally likely. So why can you say that it's a contradiction? I mean, each sequence is, from the friend's perspective, equally likely. Each possible sequence.
It's a prediction,
Yes,
not
but I mean-
about this measurement. The next one by Wigner.
About-
Yes, sure. Yes, but each. So from the friend's
I mean,
perspective,
it's
uniform. Like both are equally likely.
Yes, but I mean,
And then
if you do this 100 times, then you
yes,
always get
but
wrong.
that's exactly. So if let's say I make a prediction and say, for me, you do now 100 measurements, and I say that each outcome is equally likely. Now you get 100 times a 0. Why is this a contradiction? You just got one of the strings. It happens to be the one we call 0, 0, 0, but it's as likely as any other one. So
Someone tells you a coin is fair, you toss it 100 times, you get heads every time.
yes, I see that, but kind of there must be another assumption being introduced, because I could say any sequence was equally likely, and the fact that it's called the 0, 0, 0 sequence doesn't make it more contradictory than any other one. I could say it was also. I mean, I don't see what is special about the 0, 0 sequence.
Well, maybe to help
Compared
clarify,
to any other.
I understood the contradiction was between Wigner's and the friend's
Yes.
probability assignments, and not between the probability assignments and the outcomes.
But you will see that this, and one of those will be confirmed by, like statistically confirmed by actual records at some point. Like you can then do the measurement and then say, okay, this one of them I would say is, I would rather deem them right than wrong. But like the two predictions, like definitely, if I disagree. I mean, if I say this is 0 and 1 and 1 and 0,
Not equally likely. That's why I don't understand your questions.
No, I mean,
Each.
let's say if we didn't, we label them with 0 and 1s.
Which outputs now?
The outcomes of the measurement that Wigner does.
The Wigner
Yes,
does,
we are talking about this outcome.
Okay.
And at the end it will all be zeros, let's say. I mean, I don't remember how you called them, but let's say they are all
They are
zeros.
not equally likely. For none of the observers, it's 0. Because one says 0
Yes.
probability, the other says 1 probability for that.
Yes. So one observer says the 0 always has probability 1. That's what Wigner says.
Yes.
So he knows it's a complete 0 sequence. The friend each time says the 0 is equally likely as the 1.
No. It
No,
says
it
no,
It
opposite.
says the probability is like some epsilon.
Absolutely.
Yeah.
Of what?
Of getting
The main.
Wigner's result, that Wigner thinks it's with certainty. Frank has almost 0, says.
if you
It goes like 1 over
increase
the
the dimension,
because it's one of
they
the
give you
dimensions.
all
So the overlap
almost
is
0.
1
Yes.
over d, and d goes to infinity.
Oh, you make D large?
Yes.
Yes.
Okay, not the number of times.
No.
Well, no, they've
Yes,
said both things. They've also repeated the trials.
Yeah,
And
I
they're
was
using,
now
the law,
referring to
they're using the law of large numbers in
Yes.
place of a
Okay, so for you the
strict
relevant thing is
contradiction.
that you make D large, because I was now thinking of
sorry,
D is
yes,
fixed,
no,
and then you
it's-
make N large.
No. I mean,
Okay.
you would also make n large in order to test this properly. I would do that.
You
Okay.
have a contradiction even if it's a qubit and not necessarily a high.
But
It's
probabilistic one.
probabilistic one, yeah. It's not.
Yeah,
It's not going to
in
1 and
both.
0. It's 1
Yes,
half
and this
versus
is
1.
arbitrarily close to deterministic if you can make
Okay, but maybe
it as
I
high
could-
as you want.
okay, maybe we can do it later because it's otherwise it's more.
we have
The limit doesn't exist, but you have to be careful of that. But you can make it arbitrarily close.
Okay. Yes. Okay.
You
So
need to say, sorry, you need to say something like, for every epsilon you choose D, right?
Yeah.
That's what you're doing.
okay. So the reasons for this contradiction in the prediction, or you could say inconsistent predictions, if you want, is exactly the subjective application of the state update rule. So if I see an outcome, I say the state after me seeing this outcome should be the eigenstate. This is like pretty standard quantum theory. And if I don't want to think about whether an actual collapse occurs or whether this should be an update of my belief or whatever, what we definitely agree on is that afterwards I should use this state J to make predictions about subsequent measurement. So if I after measuring this and seeing outcome J, measure in some rotated or in some other basis with index K, then my conditional probability of outcome K, having seen J before, is this. Like, this is the standard Born rule. Trying to apply this in combination with some self-referentiality on the friend's behalf in Wigner's friend type experiments doesn't work. This is exactly what gives me these contradictory predictions. So these are the friend using the state update rule for his measurement, Wigner not using the state update rule for the friend's measurement. These predictions are, I would call them inconsistent, but I would say they are only a problem if you have an actual contradiction. If at some point one agent can actually see, Chaslov does this with the pieces of paper in the thought experiment, have two contradictory pieces of classical information. You say this should be 0 and this should be 1, and then you have one person can convince themselves that there is a contradiction at some point in the experiment, which is the case for this one, due to the possibility to exchange these outcomes and then for Wigner to actually record the statistics and then see which one is right. I'm not even committing here now to who is right in the end, but you can create a situation where by actual experimental data that at some point will be accessible to both of them, you can see that one was clearly right and one was clearly wrong.
Can I just remark that that seems to me to be a crucial part of deriving a contradiction, is making the eventual connection to the data from the experiment and seeing who makes the better predictions in some sense.
Yes. I mean, the thing is that those are predictions about the same data, and if they already contradict each other, only one of them can be right. Yes, exactly. Okay, so now, if I'm assuming universal validity of quantum theory and, of course, this in principle possibility of doing this at all, I have now a situation where one of the two will be wrong. And I would say now universal validity of quantum theory means that the unitarity does not break down inside this box, because this would require some new add-on to quantum theory to say why this closed system does not evolve unitarily. So in that case, we say that the friend can establish that she was wrong in making her predictions by using the state update rule with this self-referential statement in order to try to predict the results of super observers. Okay, why would you do that? Why would anyone do that? Well, because of decades of experimental evidence of the state update rule giving good predictions for subsequent measurements, at least if you are on what I would say the same level of observation. So I would argue a rational friend would now probably look for an alternative to the standard Born and state update rule, such that this still holds. Like for all the situations where I know my quantum predictions using standard Born and measurement update rule work very well, I want to recover that. Okay, and our proposition was now the following. So we assume, like full unitary quantum mechanics, it means any measurement is just an entangling unitary of the system and the observer's memory state, I would say, that entangles these memory degrees of freedom with the state of the system. Like you express this state in the basis that is going to be measured and then entangle this with the memory. So this 0 state is the state of the observer before the measurement, like some ready state that is orthogonal to all the other ones, which can be read as the state of the observer having seen outcome J, like having a record of J in his or her memory. Then the proposition is the probabilities of outcomes are given by the projectors of states of the observers having seen those outcomes in the state evolving according to this full unitary evolution. In a formula, you do this. You take your initial state, evolve it unitarily for all the observations that are performed, and then project on the observer having seen the outcomes you're interested in, right? And I will call those probabilities Q in order to distinguish them from the P where I use the measurement update rule. Okay, first, sanity check. Does this give my usual quantum probabilities? And yes, it does. So if I just consider the probability for one outcome, like Q of j is the same as P of j. And also, conditional probabilities for subsequent measurements of on one system are the same. So I do this. I start with the system state and two friend memories. So this is either friend 1 or 2, or one friend measuring twice and recording those in two different like registers in her memory. Evolve this unitarily, get this weird state, project onto the two outcomes, and this is then the joint probabilities of the two outcomes, and then do the usual thing to get the conditional probabilities, right? Good. And now the crucial difference, actually. If I go to Wigner's friend experiments, doing what I just did gives different probabilities. So I do the same again. We have our initial state, two memory entry, registers, where the second one is now the one of Wigner, who actually does the full operation. Then this evolves to something like this, where here we have then the state of the source, the friend, and this is now the memory state of Wigner. And then doing the same thing again, it's a lot of formula, but you can easily see that this is not equal to this, I would say, collapse probability, where the friend would update the state according to the result she actually saw, and then just project this onto the state that is going to be observed. In our simplest, we've done this in the paper for more general cases and also for Frau Renner. In the simplest version, where we have the collapse probability here. If you do this with this formalism, you get a Q of plus conditioned on J of 1, which is the same as Wigner would have predicted from the unitary evolution. But this is now independent of who uses it. So if the friend uses this type of quantum theory, she gets predictions that agree with Wigner. And in more complicated setups, that also works. So what I just said, this modified Born rule gives, for the relative state formalism, gives the same probabilities as standard quantum theory for what we call the same level of observations. So the things we see every day, like different people measuring one quantum system. But consistent predictions for the encapsulated observer case. And it does that because there is one, I would say, intersubjectively agreed upon global state from which the probabilities are calculated for all agents, so you won't get a contradiction there. And since there is no application of the state update rule, you cannot have an inconsistent application of the state update rule. Simple enough. One remark here, I said the global state, but don't want to refer to some quantum state of the universe. It just means the state of the whole experiment I want to consider and make predictions about. That's also not too much there. Yeah, a nice thing I'd like to add here is we calculated this also for Frau Renner, and our probabilities agree with the calculations of the setup in terms of generalized Baumann mechanics, which was done by Tony Sudbury in New York. And the reason for that is, as far as I understand it, I'm not an expert on Baumann mechanics, but you have this global pilot wave that keeps evolving unitarily regardless of whether a measurement happens or not, and this determines your probability. So that's why they agree for the cases for this case. We haven't checked whether they like agree in general, but I think they would. This is just an intuition, though. Okay, so now to the interpretational matters, because so far this was all purely formal, so you can read this whichever way you want. I mean, I didn't say how you should understand the states or the update rule, or like the lack of the update rule, or facts relative to whatever, but I would like to read this relative state formalism, which I don't want to link to many worlds interpretation, but just really quantum states and full unitary evolution, and read it a bit like that. So relative to the friend, having seen the outcome J, the state of the system is J, meaning that, as we've seen, she might just as well, she might just as well use this updated state for all the predictions she wants to make for subsequent measurements, as we said, inside the laboratory, or as Jeff Poop said today, the inner measurements that she wants to predict. Relative to Wigner, if he sees outcome plus, of course, this applies, but to the whole laboratory, the state is then plus, and for any subsequent measurements by other super observers, you would use this plus state then to make the predictions. And as long as Wigner doesn't observe the outcome of the friend's observation, F should use the full state for making predictions about Wigner and not use an update rule for her own state and the state of her laboratory. Yeah, these are the references if you're interested in. And thanks.
This makes a lot of sense, this rule that you explained. However, you said something afterwards where I got a bit, let's say, hesitant, because you said if we apply it, we should then not consider the state of the whole universe, but kind of the state of the system we consider. Wouldn't exactly this statement be problematic, because it would again introduce a kind of subjective concept, which would then again lead back to the problems we actually have at the beginning. So let me just make an example. If I just look at the outcome of a random number generator, and then I look at it, and maybe I make a prediction of what the same outcome will still be a second later. I mean, I just look at my piece of paper again where I wrote down the outcome. Now, I could still in some way say, let's look at, as the experiment, the whole room in which I am and so on, in which case I considered this entangled state in which I will probably be. And in this case, I would expect that my prediction will now be the one of like, as you said in this picture, kind of an outside person. So it would, and I look, what would I see again? Then it is probably 1/2. I would again see a 0 or 1.
I know, but that's the question of what do I want to make a prediction about? If you say I have this and want to check again, then I'm doing I still like evolve this unitarily, but this is another memory of the same level of observation. So this is a second observation of the same state. While I can do this, but then I will get the probabilities exactly like I would get them from the state update rule. If I'm now, however, asked to say what will Wigner out there see, I would be better off by not assuming this, like, how do you say, extending this state update rule to the whole room just because I see this here, but say, okay, no, do the whole unitary thing, including Wigner, and then I project onto the state, like calculate this according to this rule.
But wouldn't then you need to introduce some notion of, because you said I look at the state again, and so in this case I do this, so there's some notion of like looking at something again, which is not so well defined in general, because everything involves unitarily, and I could say this is just another measurement that I do. So I'm just not sure whether you're introducing now concepts which still are quite subjective. That's kind of the concept.
I mean, you can interpret this as subjectively as you want. I'm just saying if you want a formalism that allows for some notion of objective description of the setup, you should use one where there is agreement on when to apply the update rule and not. That was the point. Yeah.
But then you said this state itself is again something I can choose. That may be. I mean, in the sense that I have to choose what is my experiment. Yes, I don't.
Well, I guess you first define what you are interested in, just like in every situation in laboratory. You say, I want to talk about just spin, or you want to talk about the spin and measurement approach. You first define what is the state, what is the system you want to observe, and then you take this always the same rule and start from this level and say, okay, that's the psi of the whole system. If it is just your random generator locally, then you don't need to use this. I mean,
so you're saying once I know which measurement outcomes I'm interested in, it's uniquely defined what the system
uniquely
is.
defining what is the state, and then you apply the rule.
Okay, if that is the case, then okay, I thought the system could still be made smaller or larger.
It could be made larger, but you don't need, as long as you don't want to know about the larger things. You don't want to measure them.
Maybe later I want.
Yeah, I think
Well,
it's
if you
similar
want,
to.
then you have to. But this is not different than in quantum mechanics itself. Like if you have 2 spins, 1 spin, 3 spins, you have to know the state of the 3 spins. If you want.
Yes, but the problem is that if I go to a too large state, it will change my prediction. I mean,
no. I think there is a consistency. Like if you want to just describe your spin, then you can use the formalism. You don't need for lower level form, but I mean lower level state or high level state, and they're all consistent. So I don't need to take too many things to make a prediction about a small portion of this world.
I think it requires some kind of notion of, I mean, it's kind of a Heisenberg cat that you can introduce, but this requires some, this incorporates the possibility of having several of them, like nested ones. So it's kind of giving a framework where you can actually impose the level of observation. If you have super observers, then
so the
you incorporate this
like
into
how far you need to evolve this unitarily depends on how many levels you basically want to jump in your prediction.
Okay, there's a very concrete
not really
reason why I'm asking. So if you take the salt experiment with the 4 agents, and you ask, but you now change it in a way where the first friend who has to make a prediction about the final outcome of Wigner, just that he gets this instruction which spin it should prepare, and then should make a prediction of what Wigner gets. But he wouldn't know that this instruction was itself generated from a random number generator. So then he would not include in the description the fact that he's himself in a superposition. He just doesn't know. I mean, that's what usually would be the case in reality. I'm probably, when I use a random number or when I do something, I do an experiment to spin up, maybe there is a superposition with another thing where I actually do the experiment with the opposite thing, but I don't even know it. In this case, I would choose a description which doesn't include this thing, and that is the thing where I think one would probably get a different result.
Convinced that you're wrong.
Yes, okay, yes, that's right. Yes,
wrong.
that I agree with, but I couldn't know from the start, so I would have a choice which I cannot answer in some way.
Yeah, that's true.
Yeah, no, but I mean, in your setup, the whole protocol is known to everybody, right?
Yes, sure. That's why I said we change it in such a way that.
Then you have to.
But this is a change which, in reality, is actually the case. So whenever now, even if we talk, probably there's another branch in which you're not here, and maybe you have to consider it. Maybe not. We don't know it. And that's. Yeah, I could be proven to be wrong then if you say something in it, but in practice it wouldn't happen. We just make the wrong statement.
But that depends on what I'm supposed to predict.
Yes, but in this case it's the same prediction. I didn't change the prediction. I just changed what the friend knows about the outside world.
I think the whole thing makes uncomfortable. You don't know how to apply continuity.
Yes, exactly.
Like
yes,
you sit in your laboratory and now.
Yes, you don't know what to do because you don't know whether you need to consider the total state of the universe or only use L. Yes. Okay, but if you agree on that, that's fine. Then we just know we cannot apply quantum theory in general.
I thought one of the points of this analysis was exactly that. As long as you restrict your measurements in some sense to the local measurements within the things inside the laboratory with you, you can continue to use the usual update rule without, regardless of whether you think there's any super observers or not.
Yes, that's true.
And so that seems to restore some amount of stability to the whole thing.
The question is when you make measurements about the laboratory, and then should you believe on what you see in your laboratory as conditional that, or maybe you receive some message from an alien
that proves you wrong. Yeah. That would happen.
or tells you
Yes.
you are in that state.
I mean, are you asking whether you could conceive of a situation where you're not